start with the very good morning to all the students of B.R. Ambedkar Open University registered for Nuclear Physics C5 module. I'm Dr. T. Prasad, Department of Physics. So I'm taking the Nuclear Physics C5 module, and today we will cover the unit 13 of your C5 course, that is the phase contrast microscope. So here, what are the aims and objectives and this phase contrast microscope and its definition and its principle and instrumentation and what are its applications, we will see today. So usually, what is that phase contrast microscope? It is all type of an optical microscope. It was first described by Dutch physicist in the year 1934. And usually in the optical microscope, we have to stain the sample in the transmission so that the stain will give you the obstruction to pass the light. So that's why it is very difficult without straining. That means without a coloring, adding a color to the sample, it is very difficult. So unstained living cells absorb practically no light. That's why we will try to exploit without straining the cells. Then the light passes through the sample. But here we have to use a different technique. Okay, poor light absorption results in extremely small difference in the intensity distribution in the image. So whatever the light is passing through the transparent cells, so it is very difficult to distinguish those things. And another one is, once if you stain the cell, what will happen? It seizes. That means we are giving an external thing. So that cells is not a living one. So to make the cells barely or not at all visible in a bright field microscopy. So that is the problem with the bright field microscope. So here in this phase contrast microscope, it is also an optical microscope, but here we convert the phase shifts in the light passing through the transparent medium to the bright changes in the image. So when it passes through a whatever the transparent medium, so you will get a small phase change. That means you will get a unstrained light, and that is the undeviated light, and another one is passed through the one. Sorry for the interruption. So this phase contrast microscope is an optical microscope technique that converts phase shifts in the light passing through a transparent specimen to bright changes. So this is the picture of an optical microscope, and here you have a different parts. So here this is the image plane, and here you have this direct light. So here you have a direct light and the other is passing through the specimen. Both will have you have a constructive and destructive interference. So from this, you can get the contrast. So from that, you can distinguish within the cells of a transparent, and we can image the cells. So here the important parts are phase plate and is a specimen. So you have to keep the specimen here, the transparent specimen, without any strain. You have to keep here. And another is the condenser lens, and annular ring is also a extra uh, component, whatever you find in a phase contrast microscope. And this is the light source. So from the light source, we are illuminating the sample, or the light is passing through the annular ring and condenser, and it reaches the specimen. And here one is a undirected, there is a undeviated light, and another one is a phase shifted light. Those two will have a constructive and destructive interference, and it forms a image here. So this is the more your physical the schematic diagram of a phase contrast microscope, and this is the object lens. So you can have a 10x and 12x, the different magnification objectives. And here 2 is the specimen. We have to keep the specimen here. And 3 is the condenser lenses also incorporated here on this plane. And annular ring is provided at this fourth one. And the fifth, this is the light source. So this is how the schematic diagram of a phase contrast microscope. And this, when light passes through cells, a small phase shift occur which are invisible to human eye. So in a phase contrast microscope, these phase shifts are converted into changes in amplitude, which can be observed as differences in image contrast. Okay. So that is the actual that concept. Okay. So how it works also, again, we will see that partially the coherent illumination produced by the tungsten or halogen lamp directly through a collected lens and focused onto a specialized condenser. It is an annulus condenser, and positioned, that is, at the substrate itself, at the front focal plane of the sample. Okay, that wave fronts passing through the annulus illuminate the specimen, either pass through the undeviated or diffracted and retarded in phase by structures and phase gradients present in the specimen. So that way, whatever that phase gradients will be observed when the specimen, the thickness and other refractive index, because of that refractive index, the change, they will pass through the specimen at a different speeds, and it gives a small variation in the phase. So undeviated and diffracted light collected by the objective is segregated at the rear focal plane by a phase plate and focused at the immediate image plane to form the final phase contrast. That image you can observe through the eyepiece. Okay. So what are the different, we will go through the different parts of these phase contrast microscope. So that what is an annular diaphragm? So it is situated below the condenser. So below the condenser, we will keep this annular diaphragm, and it is made of a circular disc having circular annular groove, and the light rays are allowed to pass through the annular groove. And through the annular groove, the annular diaphragm and the light rays fall on the specimen or object to be studied. So at the back focal plane of the objective develops an image. Okay, so that is the description for an annular diaphragm. And another important component in the phase contrast microscope is the phase plate. So it is either negative phase plate or having a thick circular area or a positive phase plate. We can use any one. So this thick or a thin area in the phase plate is called conjugate area, and the phase plate is a transparent disc. So with this, with the help of annular diaphragm and the phase plate, the phase contrast is obtained in the microscope. So we will have to get the phase contrast. So that phase contrast, basically we are getting from the that resultant wave, we are getting from the undeviated as well as the deviated waves. So that's why this is obtained by separating the direct rays and from the diffracted, or that is a type of a interference. So both are possible. So the direct light rays pass through the annular groove, whereas the diffracted light ray passes through the region outside the groove. So these two will have a different refractive indices of different cell components, and they travel at a different degree and at a different velocities. So it reaches finally and forms a contrast in the imaging. So what are the applications where we are using these phase contrast microscope? So to produce high contrast images of transparent specimens such as that living cells and microorganisms and thin tissue and lithographic patterns and even fibers and latex dispersions and glass fragments and subcellular particles. So here, that's why the finally this phase contrast microscope, that is an advantage. So that means the whatever we are using the phase contrast microscope in, it is a type of a special microscope. It enables to view different transparent photoplasmic components without staining and without killing the organisms. So that's why to see the live living cells, it is one of the best one. But it has its own drawbacks. What are those drawbacks? We will see. So phase contrast condenser and objective lenses are very expensive. And so it is not possible to use in all the teaching labs, and it is quite expensive to use, except in the health profession. We cannot one cannot afford to use this one. And this one, to use the phase contrast, the light path must be aligned, so that alignment and all the other small complications are also arises. So those things we have to take care. So we will move on to the other microscopes, that is the electron microscopy. So that electron microscopy is also, it is a remarkable research tool of the 20th century. So why we are dealing with all these microscopes and all the electron microscope or scanning electron microscope and tunneling or transmission electron microscope. So these are all very useful tools for characterization. Once if you prepare a material in a material science, or to study any other living or non-living organisms or any other microstructures, that is a microstructure means within the, in a solid state physics we have, the crystal structures within the crystal, how the microstructure and the growth of a thin films. To characterize these microstructures or materials, these tools are very, very important. Okay, so how the crystal structure is formed or not, we will clarify with the X-ray diffraction. Whether it is a crystalline structure or a non-crystalline material, it is a amorphous material. So for that, we will use X-ray diffraction. Similarly, for all these material characterization, we are moving to another, that is electron microscopy, that is a scanning electron microscopy. So microstructure, what are the determined different properties? So structural properties. So in any ferroelectric domains of a barium titanate, BaTiO3, and this type of a ferroelectric, within this, after formation of a thin film or any bulk material, so that is possible to the surface morphology, how it looks like. So how the grain boundaries and what are the grains and what are the microstructural defects, all these we can get the information through these scanning electron microscopy and other techniques. So that microstructure is important one. Okay. So this is the magnification, usually from very, very high in a scanning electron microscopy. Even resolution is also up to 50 Armstrong units, and excellent depth of focus is also possible. And relatively, we can easily prepare the sample for study. And this is one of the your total setup for a electron microscopy, and this is the your instrumentation and all the associated computer controlled, and you can visualize and you can save the images that we got from the scanning electron microscopy. And what usually what is the principle? So wavelength of the matter particle can be calculate using a relation lambda is equal to h by m nu. So you know these things. So that means we are using an electron gun here. So don't make X-rays use electrons directly. And but wavelength, so lambda is hc by E naught. That is for a massless photon. And lambda is equal to h by 2m electron mass q into V naught. This is a non-relativistic. And if you make a relativistic corrections, this lambda will be equal to. So that's why this is the one of the basic relation between a energy and a lambda and Planck's constant. Okay. And lambda is equal to this. Okay. So here, all these, if you substitute the values of h Planck's constant and all the other, you will get this, and volts somewhere around 10 kV. So by using these, you can get the resolutions very more resolution is possible. So this electron microscopy. So here, what are the important parts of a electron microscope? So here you have a electron gun. So that is a variable high voltage power supply. With that, we have to use the electron gun, and from that you can produce a electron beam, and that electron beam so passes through a magnetic condenser lens, and it will have a condenser and objective condenser lens, and finally it will pass through the specimen, which is kept in a vacuum chamber, and electron detector is also placed between the objective lens and the specimen, and this is connected to your computer control, that is a CRT display or computer monitor and control unit. So these are all the different parts of a scanning electron microscopy. So that scanning electron microscopy important that has a two pairs of electromagnetic coils located within the objective lens. One pair deflects the beam in the X direction across the sample, and the other pair deflects in the Y direction. So scanning is controlled by applying the electrical signal to one pair of scan length coils. So such that the electron beam strikes the sample to one side of the center of axis of the lens. So axis of that lens we will apply. And by varying the electrical signal to this pair of coils as a function of time, so the electron beam is moved in a straight line and across the sample and then return to its original position. So similarly, the process is repeated with the other pair of coils. So that's why we can completely scan the surface of specimen, and that whatever that secondary electrons deflected out of the surface of the material will be replica of the refractive index of the surface, and thus it produces an image on the monitor. So this is the magnification. Also, you have we can get the W by R. So that where W is the width of the CRT display and R is the single width of the single line scan across the sample. So from that we can get the magnification. So by applying that magnification ranges, by choosing all these magnification ranges, we can scan the whole surface of the sample, and surface morphology we can study for a microstructural studies, for a synthesizing a new materials, or the characterization of a new material, or a synthesis and characterization techniques. So from that also we can all the phases are same or not. Also you can get the phase and these cell boundaries. So from that you can get that more information regarding the microstructural studies. So then we will move on to the scanning, transmission electron microscope. So transmission electron microscope, that instrument, so it has a source of high resistive tungsten filament, and that is heated by an electric current, and it emits a stream of electrons. So here the high voltage of electric field, almost more than 50 kV, applied between a pair of metal plates accelerates the electrons. So accelerated electrons, then they forced through a collimated aperture. So a type of aperture is placed, through that all these forced to pass accelerated electrons. So the beam then passes through the condenser, and condenser lens is a magnified coil which it corrects the aberrations in the beam and directs towards the objective lens. So from that you have a strength that greater the flow of current, greater will be the strength of the magnetic field. So from this, after that, the sample is kept below the condenser lens, and electron beam passes through it and scatters various direction of depending on the varying refractive index of the sample, whatever that we place on the holder. So the whatever that coming electron beam passes through the second set of magnetic coils, and this is known as the objective lens, and that objective lens focuses the electrons and forms an intermediate image, and that final image usually we will produce by third set of magnetic lenses, and that is called as a projection lenses. So with that we will enhance the image, and we can by projected onto a fluorescent screen, and we can view through a CRT monitor. And these, what are the applications means, usually in the field of biology, and in the field of medical, and in the field of material science, we will use these sample studies of a morphology, that means surface studies, for the these are the applications. And what is the advantage of this SEM, advantages of SEM over your tunneling electron microscope, transmission electron microscope? That is, it is a particularly SEM is useful because it can produce detailed, it's a three-dimensional images of the surface objects. But TEM gives only a 2D images, and SEM scans the surface of the sample bit by bit completely, whereas that TEM looks at relatively whole area of the sample only at once. So it will not scan from one end to the other end, it will scans the whole area, whatever it is we are projecting or we are keeping on the sample. And in the case of biological samples, specimens scanned by SEM, they don't need a thinly sliced, as they are being cut into thin slices. When we use a TEM, the specimen examined by TEM have to be absolutely dry. They must be dehydrated. So that means to prevent the secondary electrons, whatever you are emitted from the specimen, and they may scatter by water molecules in the sample. That's why these are the 3 points where your SEM has an advantage over TEM. So then we will move on to the unit 14, that is the thermogravimetric analysis or thermogravimetric analyzer. So here in this unit we will cover TGA and DSC. So TGA means thermogravimetric analysis, and DSC is differential scanning calorimetry. Okay, so all these thermal methods using thermal methods, the physical properties of the substances such as mass and heat capacity and the heat of a reaction are measured as a function of temperature. So there are two most common methods in the physical sciences. So one is TGA and another one is DSC. So TGA has two type of are available. So one is a dynamic TGA, another is static or isothermal TGA. So if the material is subjected to conditions of a continuous increase in temperature, then it is a dynamic TGA, and static or isothermal TGA is in this sample is maintained at a constant temperature for a period of time. So during a period of time, and during which any change in weight we will try to measure, or we will try to notice what is the change in the weight with the time. Okay, so what is the principle behind this? So in a controlled atmosphere, the mass of the sample is recorded as its temperature is increased linearly from an ambient temperature to around almost 1500 degrees centigrade. So after that, a plot of mass and percentage of mass. You can take mass or percentage of mass as a function of temperature. So this plot of mass versus function of temperature is called a thermogram or thermal decomposition curve. So what is the important that instrumentation? In the instrumentation, what we are using important components and how do you? So here important components are, it needs a sensitive balance and it requires another furnace. So the main components, these two, the furnace and a balance and auxiliary equipment, other equipment that is for you need a gas system to provide in an inert atmosphere. That is the ancillary equipment. And a furnace, it is a very sensitive analytical balance and a computer control the temperature and a data acquisition. So these are the important components. And here in this, usually the sample is held in a small a type of a cup and in a sample holder, and it is a completely kept in a furnace. And the furnace is connected to a temperature controller or a furnace control. And the other end of your sample holder is connected to a sensitive balance. Okay, thermally isolate the whole balance, thermal balance from the furnace. We will isolate these furnace and the balance. Okay, so whatever that variation is produced in the mass of the sample, we will take the sample and variation, whatever the variation in the mass, we will notice. And for that, we need a type of a that beam of light and imposes that light shutter between the lamp and the two photodiodes. So because of that photodiodes, the light, we will study the output of a light through the detectors, photodiodes. And the resulting imbalance in the photodiode current, and whatever that current is sensed in a photodiode will be pre-amplified and amplified, and it fed to a coil, and that coil is between a pole pieces of a permanent magnet. So the amplitude or whatever that amplified current that received at that photodiode and transformed into a information. So that current we will translate into an information regarding the mass by the data acquisition. So it's a Mettler instrument, has a several weight ranges. So you can handle very low masses also. And usually that furnace, it is very simple. You have to control the temperature within the furnace very with a fine temperature control. So then we will move on to the applications. What are the applications? So where we will use these thermogravimetric methods, so to study the polymers and other that information about the decomposition mechanism. So whatever that material of a polymer, how it decomposes at a different temperatures. So to study that, we use the TGA and thermogravimetric analysis. Okay, and yes. So then we will move on to the differential scanning calorimetry. So what is the principle of differential scanning calorimetry?